Okay, so this is section 11.3. We are going to be talking about the integral test and the estimates of sums. Um, this is going to be another test for convergence and divergence of a series. Again, the idea is we want to figure out, does the series tend to converge to a sum or does it tend to diverge because you can't find a sum? And the integral test is probably the one that tends to make the most sense because when you're talking about a sum of an infinite number of things, that's technically what an integral is. Um, this one will pretty much directly relate to section 7.8 in the past when we did improper integration. Um, there are going to be several more, by the way, tests that we do when it comes to testing for convergence and divergence. And hopefully by the time we get to the latter parts of the chapter, why we're doing all this will make sense. But for now, we're going to talk about the integral test and then the estimates of sums. Okay, the reason that that second part is in there is because it's going to be very important to understand that the integral test, while it does give you a sum, will not be the sum of the series. We can do a strong estimation based upon some integral test stuff, but it will not be the same thing. And the reason for that is, if you think about it, when you take the sum of a series, you're taking the sum of a bunch of discrete numbers. So you're going to have a term, another term, another term, another term. You're going to add all those things up, where the integral test would technically take all of those terms plus everything else in between all of those terms and add those up. So it's going to be slightly different. But they are both sums, which makes this test really convenient. So here are the criteria. You have to have a function which is positive, continuous, and decreasing. For some values, it says x is greater than or equal to 1. Technically, x can start greater than that, but that's typically where you start. And you would basically have to call a sub n some kind of a function of n. So you're going to rename your general term of the series the function of n, and then we can utilize the test. Again, it has to be positive, continuous, and decreasing when you call your series some kind of a function. If that is the case, if the integral from 1 to infinity of f of x converges, then so does the sum. If the integral from 1 to infinity of f of x dx diverges, then so does the sum. Whatever one does, the other will do the same thing. So they're either both going to converge or both going to diverge. All right, so to use this test, first of all, you have to determine if the function is a decreasing function. Most of the time, it's going to be relatively obvious. You could always use a first derivative test to see if that's the case for values greater than 1. We really don't care what happens before that. Then you're going to integrate and evaluate the definite integral. And then if you get an answer, a finite value, the series will converge. If your answer is either infinity or negative infinity or some kind of does not exist other than infinity or negative infinity, then the series will diverge. And again, right there it says this test will be good for values other than one, starting at 1 as well. In other words, you could start at 2 or 3. You have to know your domain. All right, this will definitely be a multi-video lesson because the integral test, being the fact that they are integrals, can take some time, and we are definitely going to go back through a bunch of our antiderivative techniques in order to complete some of these integrals. All right, why does that number 3 on the previous page tend to make sense? Well, a definite integral is simply a sum, like we mentioned before. And for a series to converge, the sum has to exist. For the sum to exist, the terms as n gets really, really large need to basically become 0. Again, you are basically having to add up a bunch of zeros at the end. So in short, if the integral converges, the sum converges. Just repeating what we said. And if the integral diverges, the sum diverges. They are very closely linked. Even though they are not the same, they are very closely linked. All right, so let's take a look at this. Determine whether the following series converges or diverges. So we have learned a couple of different tests for series already. The integral test may not be the first thing you want to go to. We have learned the nth term for divergence, which only tells divergence, but it's a very convenient test. You should always look at this thing and say, okay, does the limit of my nth term here, my a sub n term, does that go to something other than 0? Well, if you take the limit of n over n squared plus 1, that approaches 0. That's inconclusive, so we really can't use that one. Could I possibly make a telescoping series out of this because it's a polynomial over a polynomial? Unfortunately, n squared plus 1 does not factor nicely without using imaginaries, and we are not doing that. So no, we cannot use telescoping here. Is this a geometric series? Well, it's clearly not a geometric series because there's no constant value being raised to an n power. So those are pretty much the ones that we've done so far. We've exhausted those possibilities right there. So let's look at the integral test because it's pretty easy to see that that this one, right, well, I won't say it's pretty easy to see, but it is relatively something you should be able to recognize you can take the antiderivative of easily. Okay, is it going to be a continuous positive and decreasing? Well, it's positive because all the values of n are going to be positive. Everything you're plugging in is going to be positive. It's continuous if you create a function out of that because nothing makes your denominator 0 in the real number system. And the only other thing you would have to check for is it decreasing? And that's a little bit tougher. I am not going to show the entire first derivative test here, but this one is a decreasing function. So let's go ahead and apply the integral test. And the integral test says that if we take the integral, we are going to state those criteria, by the way. We're going to say this is positive, decreasing, and continuous. Okay, so it says if we take the integral from 1 to infinity, I know I'm starting at 1 because it says n equals 1 is my starting point, now we have to create a function of x. Well, we're going to let f of x be this thing right here. We're just going to replace it with x's instead of n's. Technically, you could use n's, but I like to replace it with x's. So it's going to be x over x squared plus 1 dx. Now, as we know, we cannot actually take an integral to infinity. But what we can do is we can take an integral from 1 to some finite value, t, and then take the limit as t goes to infinity. So that's what we're going to do. We're going to take the limit as t goes to infinity of the integral from 1 to t of x over x squared plus 1 dx. And this is going to be a basic u substitution. Your denominator here will be u. So x squared plus 1 is u. Du then will be 2x dx, making dx du over 2x, which is good. So let's go ahead and write this. The limit as t goes to infinity, integral from 1 to t of x over u times du over 2x. Technically, my bounds are incorrect. I should probably not have written those bounds on there, but we're going to change them real fast because that is going to get rid of that. We're going to have the limit as t goes to infinity, integral from 1 to t. Now, oops, can pull the 1/2 all the way out to the front, all the way out to the front of the limit, actually. And then we're going to have 1 over u du to take the antiderivative of. Once I take the antiderivative and substitute back in the original x values, my bounds will be correct. So again, technically what I have there is not correct. I probably should have left the bounds off, but we'll deal with it. limit as t goes to infinity. Antiderivative of 1 over u is a natural log of the absolute value of u. But u here is x squared plus 1. Technically, because x squared plus 1 is always positive, I don't really need the absolute value, but I'm going to leave it just to be safe. And I'll evaluate that from 1 to t. So we get 1/2 the limit as t goes to infinity of the natural log of t squared plus 1 minus the natural log, plugging a 1 in, of 2. Okay, natural log of 2 is no problem whatsoever because that's just a finite value. The problem is the natural log of t squared plus 1 as t goes to infinity is just going to make the argument of the natural log bigger and bigger and bigger, which increases the value of the natural log to infinite values. So we're going to have basically infinitely large values minus the natural log of 2, which is still going to approach infinity. Multiplying it by half still makes it approach infinity. So this means since the integral itself approached infinity, the integral would be divergent. Therefore, the sum is also divergent. All right. Hopefully that didn't confuse anybody too much there with the process there. Again, the basic idea is you're finding the integral. If the integral converges, the sum converges. If the integral diverges, the sum diverges. This is honestly probably one of the last tests that I would go to unless I had to use it because it's just kind of a cumbersome and long test to do. All right, determine whether the following series converges or diverges. Once again, go through all the different tests that you've gone through that we've done so far. That's not geometric. There's no possible form of geometric here. Can't do telescoping because n squared plus 1 does not factor. And this is definitely a positive decreasing and continuous function. So it looks like that is going to be our best bet. This is positive, continuous, and decreasing. Okay, and this one is pretty obvious. There's no real test you have to do there since the numerator doesn't change and the denominator gets bigger and bigger. That's pretty obviously decreasing. So let's go ahead and try the integral test. Once again, the integral test says we're going to take the integral from 1 to infinity of 1 over, in this case, x squared plus 1 dx. Okay, so this one is not going to be a u substitution because I don't have that extra x on top to get rid of when I take u to be x squared plus 1. You basically just have to recognize this. This one has to be one that you say, oh, that's the form of the derivative of the inverse tangent. So that's going to be what we're going to do. So let's set it up the correct way. It's the limit as t goes to infinity of the integral from 1 to t, 1 over x squared plus 1 dx. No u substitution necessary. The antiderivative of 1 over x squared plus 1 is inverse tangent of x. So we are going to get the limit as t goes to infinity of the inverse tangent of x from 1 to t. Plugging in t and plugging in 1, we'll get the limit as t goes to infinity. And it is important to have this limit on there because otherwise it's not the proper, the correct improper integral is the way I should say it. This will be the inverse tangent of t minus the inverse tangent of 1. Okay, the inverse tangent of 1 comes straight from the unit circle. We should pretty much know that the inverse tangent of 1 is pi over 4. Okay, that's just a value. The inverse tangent of infinity, that's one you're going to have to think about. You have to kind of know the graph of tangent. So remember that tangent looks something like this. And the values of tangent that seem to be approaching infinity are going towards infinity when tangent over here is approaching pi halves. That's where its asymptote is. So the values of tangent approach infinity as the x values or the angle values approach pi halves. So that means that the inverse tangent evaluated at infinity, for lack of a better way of saying it, is pi halves. And therefore we get pi halves minus pi fourths, which is pi fourths. That is a finite value. Because that's a finite value, the integral itself converges, which means the series will also converge. All right. I hope, again, this is not anything that's not making sense to this point. I think we're going to stop our video there. Again, I said this is going to be a multi-video lesson. This is definitely going to be a few of them. We'll stop it there and we'll come back and do some more examples.